Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello students, welcome to the TV learning program. I'm Teacher Pasco and today I will be with Senior 4 Chemistry students. In the previous lesson, we discussed the variation in the physical properties of elements in the periodic table. The physical property we discussed is the atomic radius and the ionic radius, how they vary in the periodic table. Now I have a question to ask you. How does the atomic radius vary as you go across the period? I will give you some seconds and you think about it. How does the atomic radius vary as you move across a given period in the periodic table? If I remember well, that was one of the questions I gave you for the homework. All right. As you move across the period, the atomic radius decreases. Why does it decrease? It is because of the other factors we have seen. We have two factors, the nuclear charge and the screening effect. As you move across the period, the nuclear charge increases. Why? Because the number of protons is increasing. But the screening effect remains constant because the number of energy levels is not changing. So there is no repulsion between energy levels because we don't have a new energy level added. So as the nuclear charge increases while the screening effect remains constant, we find that the atomic radius will go decreasing because electrons are experiencing a stronger and stronger attraction. That is the basis of the new property we are going to study today. And the new property we are going to study today, and the title of our lesson is Variation of Ionization Energy and Electronegativity in the Periodic Table. Trends in the variation of ionization energy and electronegativity in the periodic table. Before we start our new lesson, there is an exercise I want you to try. It is a revision, a simple revision for some previous topics we have covered. What is first ionization energy? The lesson of today is trends in the variation of ionization energy. Before we discuss how ionization energy varies in the periodic table, let us first define or recall what is ionization energy. So you will define first ionization energy. Number two, you write an equation for the second ionization of magnesium. And number three, you write an equation for the process which occurs when chlorine gains an electron. You write an equation for chlorine gaining an electron. You have 1 minute to finish. Okay, hope you did it well. Now let us have a look at the answers. Here we have the answers. The answer for the first question is Ionization energy, first, ionization energy is the minimum energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. The minimum energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. And the answer for the second question, we have magnesium. Remember, it is the second ionization energy, so we start with magnesium 1 positive, which loses 1 electron to become magnesium 2 plus. You should always remember to include the state symbols. Number 3, we have a half mole of chlorine molecules, which gain 1 mole of electrons to become 1 mole of negatively charged ions, and all the particles in the gaseous state. Thank you very much for doing well the exercise. Now we can start our new lesson. Here it is said that ionization energy is the minimum energy required to remove electrons from atoms. And here is my question. Do you think that the energy required to remove an electron from all atoms in the periodic table will be the same? The answer is no. The energy cannot be the same. Why? Because atoms do not have the same nuclear attraction. And because of that, electrons do not experience the same nuclear attraction. So some of the electrons will experience a stronger attraction, while other electrons will experience a weaker attraction in various atoms. So how will that change in the periodic table? We will use the atomic radius to see and explain how the ionization energy varies in the periodic table. First of all, let us have a look at the data. Variation of ionization energy across period number 2. Here we have the second period, and these are the values of ionization energy in kilojoule per mole. For lithium, we have 520 kilojoule per mole. Beryllium, we have 900 kilojoule per mole. As you go on across the period, on carbon, we have 1,090 kilojoule per mole. On fluorine, it is 1,680 kilojoule per mole. And on neon, it's above 2,000. So we can easily see that the values are increasing as we move from one group to the next. So why is it like that? Try to think about it. Why is it like that? Why is the ionization energy increasing as we move across the period? Try to use the change in atomic radius to find why that energy is increasing. Good. This ionization energy is increasing because of one main reason. It is because as we move across the period, the atomic radius is decreasing. Remember, the atomic radius is decreasing because electrons are experiencing a stronger attraction. They are strongly pulled towards the nucleus. As they experience a stronger attraction, it will be hard to take them off from the nucleus, the attraction force of that nucleus. So it requires a lot of energy to remove those electrons. As you move across the period, from one element to the next, the nuclear attraction is becoming stronger and stronger. the electrons are experiencing a stronger, much more stronger attraction. So if you want to remove an electron, you have to use more energy. And that is the reason why, as you move across the period, ionization energy increases and increases. I think that is clear. Yes? Good. Moving across the period, ionization energy increases. Why? Because the energy required to remove electrons is becoming higher and higher, simply because the electrons are experiencing a stronger attraction. The nuclear charge is increasing, but the screening effect is constant. But then there is something I want you to look at. Look here, please. We are saying that generally the ionization energy increases as we move across the period. But some elements are exceptional. Where do you see an exceptional value? In the periodic table, there are some groups where we will have some exceptional values. And in the table we have here, we have two values which are breaking the general trend. Which values are those ones? We have beryllium, we have nitrogen. Beryllium has 90 kilojoules per mole, and boron has 800. Sorry, here I said 90, it's not 90, it's 800, 900, sorry. And here we have 800. On nitrogen, we have 1,400, and oxygen, it is 1,310. So why are those two elements exceptional? To answer that question, I want you to remember how we write the electronic configuration of elements. The electronic configuration of beryllium, it is 1s2 and 2s2. This is for beryllium, and for nitrogen, it is 1s2, 2s2, and 2p3. So what is so special with both electronic configurations we have here to make the first ionization energy exceptionally high? Look at this orbital, the last orbital. It is full. Remember, we have studied that full orbitals are always stable, very stable. So for a stable orbital, it is a bit difficult to remove an electron. Why? Because you are trying to disturb a stable electronic configuration. So if you are trying to disturb a stable electronic configuration, then there will be a resistance. And to overcome that resistance, you have to use more and more energy. And that is the reason why on beryllium, we are using an exceptionally higher ionization energy than expected. And that is the reason why beryllium has higher first ionization energy than boron. Boron, which has a bigger nuclear charge than beryllium. But here beryllium has a stable electronic configuration. So to remove an electron from that stable electronic configuration, we use higher amount of energy than expected. Now, what about this nitrogen? Nitrogen doesn't have a last orbital which is full. But even though it is not full, it is half full. Remember, we have seen that in unit number 2 that half-full orbitals and full orbitals, they are always very stable. So this thing applies even in the ionization energy. As we move across the period, we find those two groups which have exceptionally high first ionization energies. Why? Because we are removing the first electron from orbitals which are very stable, which are thermodynamically stable. So this one is half full, and this is full. So the exception we have here, exception, group two elements show abnormally high first ionization energy because the first electron is removed from a full orbital which is thermodynamically stable. The first electron removed from those elements of group 2 is removed from a full orbital which is very stable in terms of energy. It is thermodynamically stable. So you have to force. You use a lot of energy than what you would expect. And for group 5 elements, it is the same, but for a different reason, but which is also based on the electronic configuration. It is because the first electron is removed from a half full orbital, which is also thermodynamically stable. Thermodynamically stable. I think that is very clear. So let us now have a look at what happens when we move down in a given group. Let us use the data we have here. Here we have the ionization energies in group 1 and group 7 to compare what happens in metals and non-metals. Group 1, we have hydrogen, lithium, sodium, potassium, rubidium, and cesium. Ionization energy in kilojoule per mole, we have for hydrogen, it is 1,310, lithium 520, sodium 490, and for cesium, it is 380. So it is decreasing as we move down the group. That is for metals. Is it the same for non-metals? Let's have a look. Ionization energy in kilojoule per mole. For fluorine, it is 1,680. Chlorine, 1,250. And when we go on up to iodine, we have 1,010. Even in non-metals, it is decreasing as we move down the group. How can we explain that? Using the variation of ionization energy. How can you explain that? Think about the explanation, please. Some seconds and you think about the explanation using the variation of ionization energy. Well done. When you consider the variation of atomic radius as you move down the group, you see that it increases. Why does it increase? It increases because the nuclear charge is outweighed by the screening effect. Electrons are going further from the nucleus because the screening effect is becoming stronger. Electrons are not experiencing a stronger attraction, so they go far from the nucleus, increasing the atomic radius. And that will have an effect on the ionization energy. If electrons are not experiencing a stronger attraction, then it becomes easier to remove them, to take them off. And that is the reason why, as we move down the group from hydrogen, which has one energy level, to lithium, which has two energy levels, the size is increasing. Electrons are experiencing a weaker and weaker attraction, and then it becomes easier to remove the electron. I think that is very clear, very easy to understand. The size increases, it requires a small amount of energy to remove the electron which is not strongly attracted. The electron which is loosely held. The electron which is far from the nucleus. Okay? Good. Here we have to say that when you move down the group, we have no exceptions. We have no exceptions, just like what we have when you move across the period. Now, let us have a look at the first part of our lesson, electronegativity. What is electronegativity? Do you remember electronegativity? We used this term, electronegativity, to define or to classify covalent bonds into pure covalent bonds and polar bonds. What is electronegativity? Try to remember what electronegativity is, please. Some seconds. Let me put it on this side so that you can have more chance of looking at the data we have here. Electronegativity is defined as a measure of the tendency of an atom to attract towards itself the bonding pair. When you have an atom here and another atom joined by a chemical bonding, one atom will have a greater tendency of attracting the bonding pair towards itself if it is more electronegative. So, how does that electronegativity vary when you move across the period and when you move down the group? That tendency of attracting bonding pairs towards themselves, how does it change in the periodic table? We can use atomic radius to explain how this electronegativity changes. Sorry. First of all, let us have a look at the data we have here. From lithium, we have 1.0, beryllium 1.5, boron 2, carbon 2.5. Generally, it is increasing as we move across the period. What happens when we go down the group? Let's consider the group of halogens, group number 7. 4, 3, 2.8, 2.5, 2.2. It is decreasing. So electronegativity increases across the period generally and decreases down the group. Why is it like that? Think about it. Why is it increasing as we move across the period and decreasing as we move down the group? Remember, use the definition to find the reason why it is changing like that. And you also combine that definition with the variation of atomic radius. It is a tendency of attracting the bonding pair. And as we move across the period, the atomic size or the atomic radius decreases. It is decreasing because the atom is getting more or a stronger nuclear attraction. It is getting a stronger nuclear attraction, so the electrons experience a stronger attraction too. And because of that, if the atom can attract its electrons more strongly, it will even be able to attract more strongly the bonding pair. If it can't attract its electrons, its own electrons, more strongly, it won't even be able to attract the bonding pair more strongly. So as we move across the period, electronegativity increases. Why? Because the atomic radius is decreasing and the nuclear attraction is becoming stronger. As we move down the group, electronegativity decreases. Why? Because the size is increasing. Electrons are experiencing a weaker attraction, and so will the bonding pair. So, generally, moving across the period, electronegativity increases, and when you move down the group, it decreases because of the variation in nuclear attraction. I hope you have understood everything, and now we can take our time and go to the homework. We have a homework you will try. We have 3 questions. Question number 1, explain how ionization energy varies down group number 7. We have seen how the ionization energy varies down a given group. Down group number 7, how does it change? That is what you will explain. You will try to give a detailed explanation, please. Number 2, why is the first ionization energy of beryllium greater than that of boron? Remember the exceptions we have seen. And number 3, explain how electronegativity varies in the periodic table. When we ask the question in general, periodic table, you will remember to explain across the period and down the group. Thank you very much for your attention. Thank you very much for your time. I hope to see you next time for the next lesson.